we have seen four closure properties of regular languages, and they are string reversal, complementation, concatenation, and cleaning iteration. And today we are going to prove that regular languages are claused under intersection, union, and set difference. So more closure properties of regular languages. First property today, regular languages are claused under intersection. And we can try to understand this by using an example. So here two DFAs are given. So this is the first DFA and this is the second one. Say A and B. Can you see what language is accepted by this automaton A? This accepts set of all strings with the odd number of A's. It's easy to see that. So what about the language of the automaton B? It's even number of B's. So that is the languages for A and B. Odd number of A's is accepted by A, and B accepts something if the string contains even number of B's. Now an interesting problem here is, can we get an automaton from A and B? A is this automaton, B is this automaton. For the language, odd number of A's and even number of B's. A string should contain odd number of A's and even number of B's. Then only the required automaton should accept. So which is basically the intersection of these two languages. And one thing that we can do is run both A and B in parallel. Given an input, run both A and B in parallel and accept if both the automaton A and B accepts. For example, consider the input string BAB, and we want to see whether it is in the intersection or not. So for that we need to run both the automaton A and B in parallel. First consider the execution or run for BAB in the first automaton. So for B it starts from Q0, for B it goes to Q0 itself, and from Q0 for A, B then A, it is taking you to Q1, which is a final state, and from there on a B you stay back, and so this is the run. So what is the run for the same input string in the B automaton? It's here. You start at P0, B is taking you to P1, from there A is taking you back to P1 again, and from there B is taking you back to P0. So that's it. So for this input, both the automaton A and automaton B accept. So this is an accepting run because it ends in a final state. This is again an accepting run. So you can accept the input string because which is accepted by both the automaton, and so it is in the intersection. Now the question is, can we construct a single automaton which accepts the intersection of the languages? We can do it, and it is by using an algorithm which is known as product construction algorithm. So remember, these are the corresponding runs in A and B, and we are kind of running both in parallel. And the idea is to construct an automaton in such a way that the run will look like this. The first state will be the pair of states Q0, P0. From there, it goes to another state which is a pair Q0 P1, likewise it goes. Don't worry, we can see how can we do it. So consider that we need to run both the automata A and B in parallel. And so where A starts at Q0, where B starts at P0. So the idea is start from an initial state, which is the initial state of both A and B, that is Q0, P0. And now you see where you go for A. For A, you can see that in this state from Q0, A takes you to Q1. That is A takes you to Q1. And from P0, A takes you back to P0. So the next state is P0 to P0. That is Q1, P0. So you see from Q0 where you are going for A, that is the first state. From P0, where are you going for A? That is the second state. Okay, so now the A transition is defined for the product automaton from this state. Now the B transition. Just verify that it is correct. So this B transition is telling from Q0 in the first automaton you are going to Q0. Yes, that is correct. And from P0 on B you are going to P1. Is that correct? P0 to P1. Yes, it's correct. So this is again correct. Now go and complete the transitions in this state. First for A, it's saying you are going back. Is that correct? From Q1, A taking you back to Q0. Yes, that is correct. And from P0, A is taking you back to P0 itself. So P0 to P0, that again is correct. Now similarly, you can complete it for the rest. For example, maybe we can look at two more examples. From here, the B transition. Q1, B is to Q1. Q1B, yes, that's correct. And P0B is P1, is that correct? P0B, P1, yes. So this is again correct. So this state is now completed by defining all its transition. Now move on to this state and see. A transition is taking you here. Why? Because from Q1 on A, you are going to Q0. So this is correct. And now from P1 on A, you are staying back. So P1 on A to P1 itself. So this is again correct. Now you want to have the B transition from here. Sorry, B transition is taking you to this state. Is that correct? Q1 to Q1 for B. Yes, that is correct. P1 to P0. P1 to P0 for B. Yes, that again is correct. So now this is again completed. Only one more state to be completed. A transition is taking you to this state. Is that correct? Q0 to Q1 on A. Q0 to Q1 on A. Correct. And P1 to P1 on A. Is that correct? Yeah, it's correct. So A transition is over, and one more transition we need to define from here, and that is for B. B is taking you back here. Is that correct? Q0 to Q0 on B. Yes. P1 to P0 on B. P1 to P0 on B. Yes. So this is correct. So the product automaton is almost completed. Now the only thing is we need to decide which all are its final states. Okay, this product automaton is going to accept the intersection of the languages accepted by A and B. So what will be a final state? A state is final if both the states are final. That is, if the first state is final in the first automaton and the second state is final in the second automaton, then you can make that a final state. Okay, this is a pair. Each state in the product automaton is a pair where the first one comes from the first automaton and the second one comes from the second automaton. And in order to accept the intersection of the languages, both must be final states. That is, the first must be a final state from the first automaton and the second must be a final state from the second automaton. If that is the case, then you make that a final state. And here you are getting only one final state. In every other case, here the first one is not a final state from the first one, so it's not final. And here again, because of Q0 non-final. And here why is it? Q1 is final, but P1 is not final here. So if both are final, if this is a final state here and this is a final state there, so we made this as a final state. So that is how you construct the automaton, and now you see the run for BAB in this automaton, BAB. So this is BAB, this is the run. Okay, BAB, and see that this is exactly what we have shown here. So first state is Q0 P0, Q0 P0. Then on a B it goes to Q0 P1. Then from there on an A you are going to Q1 P1. Then from there on a B you are going to Q1 P0. Each one is a final state in the corresponding automaton. And that's it. Hope you followed. Otherwise, please watch it again and try to understand what is going on. So we have constructed a product automaton. So it tells us that given two DFAs, A and B, then we can construct an automaton which is the product of A and B, such that the product automaton accepts the intersection of the languages accepted by the given automata A and B. So and now we can formalize. Given DFAs A and B, what is A? Q is the set of states, small q0 is the initial state of A, small delta A is the transition functions in A, capital F sub A is the final states in A. In this example, only one state, but in general there could be many. And B, where capital P is the set of states, small P sub 0 is the start state, and delta B represents the transition functions in the automaton B, and capital F sub B represents the final states in B. Over the same alpha set sigma, here AB in both the cases. Then one can construct a product automaton C such that what is the state of C? Cartesian product of Q and P. That is, a state is a pair of states where the first comes from this state set and the second comes from this state set. And this is how you mathematically define it. And what is the initial state of this automaton? Which is a pair Q0 P0. That is the initial state of first automaton and initial state of second automaton, Q0 P0. And delta C is the new transition function that we have to define. And final state, what is final state? A state is final if both the first one is a final state from the first automaton and second one is a final state from the second automaton. So this can be mathematically defined as FA cross FB. That is, the first must be a final state in the first automaton and the second must be a final state in the second automaton. So that's it, and now it reminds us to see how you define the transition function here. So what we did is, if you want to see from Q0 P0 on A where you go, you see here on A where you go, that is delta A of Q0 comma A. That's exactly what I said, delta A of Qi comma A. Similarly here you say delta B of P0 comma A, that is P0 comma A, that is delta B of the second state. Sorry, there is a typo, it should be PJ. Maybe I can change it. Okay, this is wrong, this should be PJ. Okay, PJ comma A. So that's it, and this final automaton accepts the language which is the intersection of the languages of A and B. And if you want, you can prove the completeness and soundness of this construction using the principle of mathematical induction. So this tells us that regular languages are closed under intersection because given two DFAs A and B, you can construct a DFA C such that the language of C is the intersection of the languages of A and B. With this, let us proceed to the next property, which is union. So you can prove that regular languages are classed under union, meaning if L1 and L2 are two regular languages, then L1 union L2 is again a regular language. Here again we can use the product construction. Consider the same automata A and B and languages. These languages, suppose we want to accept the union of these two, that is accept a string either if A is an odd number or B is an even number. So how can you do that? You construct the same product automaton. It's exactly the same automaton, but final states are not defined. Remember, here we need to accept if either A accepts or B accepts, because we need to generate the union of the languages. So it's either in the language of A or in the language of B. So how will you decide the final states? And that is the only difference. In the previous case, we decided a state as final if the first one is a final state from the first automaton and the second one is a final state from the second automaton. And that's because we wanted both the automata to accept. But here we can accept if either A accepts or B accepts. So a state is final if the first one is a final state from the first automaton or the second one is a final state from the second automaton. And hence here this is a final state because the second one is a final state from here. And this is final because the first one is a final state from here. The other condition also satisfied, that's fine. And this is a final state because the first one is a final state from the first automaton. This is not final because the first one is not a final state from the first automaton and the second one is not a final state from the second automaton. So both the automata rejects in that case. So that's the construction. The only difference is that in the definition of set of final states. Here a state is final if either the first state is a final state from the first automaton or the second state is a final state from the second automaton. And the formal definition goes like this. Given D of A and B, you can construct a product automaton. The only difference is in the definition of the final states. So what is it? Either the first state is a final state from the first automaton or the second state is a final state from the second automaton. In this case, the second state can be any state from here. And in this case, the first state can be any state from here. And that is how we write it mathematically. Hope you follow. Otherwise, watch it again and try to understand what we have done. And the transition function is exactly the same as the previous case. And in this case, the language is the union because we accept if anyone accepts. And with that, let us move on to the last operation that we consider in this class, which is set difference. So we can prove that regular languages are classed under the set difference operation. That is, if L1 and L2 are regular, then L1 minus L2 is a regular language. And I am giving you this as a homework exercise. We can use a product construction. Here again, you can carefully decide the set of final states. So the set of final states can be carefully decided such that the language is the set difference of L1 and L2. So please do it. And with this, I am moving to the last slide where I am giving you an assignment. This is just an exercise for you to practice and understand what is a product construction. So consider the following languages. First language is set of all strings over AB said that the number of B's is even. L2 again strings over AB said that the number of A's is a multiple of 3. That is the number of A's, if you count only the number of A's, it must be a multiple of 3. That's it. So these two are languages and you are asked to design DFAs for L1 and L2. So the first part is you are going to prove that these are regular languages by giving DFAs. And then prove that their intersection is regular by constructing the product of the DFAs that you are going to design. Okay, that's it. So in this class, we proved that regular languages are classed under union and intersection. And with your homework exercise, you can prove that regular languages are classed under set difference. So we have seen many cluster properties now. They are string reversal, complementation, concatenation, clean iteration, intersection, set difference, and union. Thank you.